What's up, everybody? Mr. Murray here, Mr. Murray's Mathland, and today we are taking a look at how to sketch the graph of the derivative of a function if you have the graph of the original parent function f of x. So let's just jump right in here. I've got three different examples here. So hopefully you see a good variety here. The first one here, notice we have kind of a piecewise looking series of line segments that are all connected here. And keep in mind, probably the word you most associate with the derivative f prime is slope, right? It represents the slope of the original function. So if you've got linear segments and you're trying to sketch its derivative, think about the slope of each of those segments. And there are no numbers here, so there's no scale, so I don't know exactly what these slopes are. But if I was looking at this, starting on the far left here, this slope is certainly a positive quantity, correct? And then it's a positive quantity, and then it changes suddenly, and hopefully you're noticing, hey, that's a cusp. The derivative does not exist there. Not differentiable, but it changes to another positive slope line segment, and that is also positive, but it's less. It's certainly less, right? It's less steep, so it's going to be a smaller positive slope than the first segment. And then the slope of this third segment, it's a constant, it's horizontal, it's flat. The slope is 0 of that segment all the way through. And then this last segment is definitely a negative slope. You're going down. And as far as trying to judge how negative that might be compared to these two positives, I would say it looks pretty similar to what this segment was, just in the negative direction. So we're going to put all that together here. And as we said, we're thinking about the slope. So this first segment has a positive slope. So, I mean, think about what that equation would be. If you want to think numerically, the equation of that line might be like y equals 5x, plus 20 or something. But the derivative of that 5x is going to be 5, right? So f prime is the slope of that. And so that's some positive constant. And so what I'm going to draw is a positive constant. So above the x-axis in the positive territory, there's no scale. Again, I have no idea how high to draw this segment, but it's some horizontal positive constant. Like we said, maybe that represents y equals 5 if that equation was 5x. And right up until you get to this cusp spot here. Not that you have to draw that dashed line, I'm just trying to line things up and show you where it lines up. And we're going to have an open circle on f prime because the derivative does not exist at that sharp point, that corner, that cusp, whatever you want to call that. It's not differentiable. All right, so now let's draw the next portion here. So on f, we have that next piece is another line segment with a positive slope. So we're going to draw another positive constant, another horizontal line above the x-axis, but it certainly should be lower than the one I've already drawn. So right in line with that cusp here, right at that same location, I'm going to have another open circle and then another positive constant all the way until we get in line with that other cusp here where it changes to that other line segment. So I'll say that's about there. I'm not going to draw the dotted line for each time. You get the idea. In fact, maybe now I'll take that away so it's not even there. And again, this vertical placement of these doesn't really matter. This one could have been higher or it could have been lower to start with, but all I know is that this second one had to be lower than the first one because this slope was certainly less than this. How much less, I don't really know. And that's about as exact as I'm going to be. Okay, and so then this third segment here, as we said, it's horizontal, its slope is 0. So I'm going to draw a line segment on y equals 0, right on the x-axis, right up until I'm in line with that other cusp where it changes to that negative slope. And then for this portion right here, it's a negative slope, so I'm going to draw a negative constant. Right? If that segment had an equation of y equals negative 3x, then its derivative would be y prime equals negative 3. So a negative constant, so below the x-axis, and like we said before, maybe roughly about the same distance away as this one was, because maybe this slope and this slope were about the same, absolute value. So roughly right about there, and then all the way to the end. And there we go. So that is f prime, and the original here was f. So there we go. So that's one example here. Now let's take a look at a polynomial example. So again, this graph is f, and we're going to sketch f prime. So there's a lot of ways to kind of start with this. One thing I like to start with is just like when you have your equations and you're trying to describe intervals where a function might be increasing or decreasing. The first thing you do is find the critical numbers, right? Where's the derivative 0 or undefined? So I'm actually going to kind of start in the same way, keeping in mind that this is f I'm looking at. So f prime being equal to 0 would be these places where it's got a horizontal tangent line. So one right there, one right there, one right there, one right there at that saddle point. Hopefully you didn't miss that, right? And these are all the places where f prime is equal to 0. And there's no place where f prime is undefined on this. So there's only that sort of critical number on this polynomial. And now, those places, f prime is 0. So what I'm going to do is, right in line with those, I'm going to make those zeros on the f prime graph I'm going to draw. So I'm going to start by putting zeros or x-intercepts right in line, right at that same x value, whatever it is. You don't have to draw the dashed line if you don't want, but I'm just drawing it for emphasis to show it lines right up with that. Okay, so our f prime graph is going to have 4 zeros, 4 places where f prime 0 on the original. And now we'll just kind of connect the dots. Well, where's the rest of the graph? So one way to think is to start anywhere here, maybe start on the left side, and just think about this. What's happening to the left of that first 0 is that f is increasing, right? F is going up, so f prime is positive. So my f prime graph I'm going to draw should start above the x-axis. That's the positive y values for f prime. And after that, f is decreasing, so f prime is negative. So we're going to start above the x-axis. F prime is positive. And then I'm going to, at that 0 that I've already drawn, I'm going to cross the x-axis into the negative territory. Now these f prime values are negative. These negative f prime values correspond to these negative slopes on the original. And right here, again, is where f prime is 0 again. So f prime is negative in between there and there. So until we get to the spot, f prime is 0, which is why I put a 0 right there. So that means my f graph has to turn around somewhere. Now I could have had that, depending on the steepness of the graph I drew, I could have had that turn around a little bit lower, a little bit higher. Without a scale, without an equation, there's really no way to know. But I know it's got to have this behavior where I cross the x-axis and I turn around somewhere. Again, it could have been down here or here, but then I'm going to hit 0 again. And then f prime is going to be positive because f is increasing again. So I'm going to cross the x-axis again into the positive territory. Now f prime is positive, corresponding with these positive slopes, right? Negative, 0, positive. So f prime graph below the x-axis, on the x-axis above. And then, keep an eye out here. The slope is positive, f is increasing until we get to here. And so my f prime graph should be turning around somewhere because I've got to hit that 0 again. And then f prime is going to be negative after that because f is decreasing. So I'm going to turn around somewhere. Again, how high it kind of depends on the graph you're drawing. But I'm going to turn around somewhere, try to make it happen naturally, kind of smoothly, and cross the x-axis at that 0. Okay, so we're getting the hang of this, right? And I've got this other 0 here from this saddle point, as we call it. This f prime was 0, had a slope of 0 at that spot. The slope was negative, the slope was 0, the slope is still negative, right? It's not a max or a min, so f prime does not change signs. So what do we draw? We're in the negative territory for f prime. We're below the x-axis. And then we have to turn around because we have to get to that 0. But we're not going to cross the x-axis because the sign doesn't change. So we just bounce off of it. And then you should be staying in the negative territory the rest of the way because your graph, as it appears, f is decreasing the rest of the way. So there we go. That is f prime. And a few interesting notes here. That for one, that little spot there where we kind of bounced off of the x-axis, you may recall that this sort of behavior, this saddle point, happens when you have kind of a cubic function or a multiplicity of 3 of some kind of 0, some kind of solution. So if you think about that as being x cubed, the derivative of x cubed is x squared, or even if you want to say negative x cubed if you look at this behavior. And the derivative of negative x cubed is negative 3x squared. So when you have that saddle point, its derivative is always going to be kind of bouncing off of the x-axis, like a multiplicity of 2, because you've decreased it by 1. If you have this sort of relative max or relative min on the original, f prime is going to be crossing the x-axis, right? Changing signs. So here's another little thing, which sometimes is useful and on the more complicated graphs, that, okay, I drew f prime kind of naturally without ever once thinking about the concavity of f. But if you happen to look naturally here, the maxes and mins on f prime, the maxes and mins on f prime, so the blue graph I just drew, so this relative minimum on f prime, this relative maximum on f prime, this relative minimum, and this 0 was itself a relative maximum. You should notice that where do they happen to correspond to on the original graph? Right there, that lines up there. And I didn't do anything special, I just kind of naturally drew the graph. Where do those happen to happen? Those are the inflection points on the original. And that should make sense because for this region right here, right there, when f prime is decreasing and then changing to increasing, that means its derivative, which would be the second derivative, is changing from negative to positive, and that means the original should be changing concavity at that spot. So I may not have had it perfectly lined up because I really wasn't trying, but that should be not a coincidence that that's going to happen. See that inflection point roughly on the original changes from concave down to concave up because f double prime just changed signs there. This one right here where f prime changed from increasing to decreasing, the original changed from concave up to concave down, right around in that neighborhood. This right here, f prime changed from decreasing to increasing, the original changed from concave down to concave up for that little portion right there. That's concave up, and then changes to concave down right here at that relative max. So it can kind of help convince you of your graphs, but that's not essential. That's kind of like a second level understanding of some things that comes in on the AP later. But let's take a look at this one. This one's kind of a mishmash. It's got some vertical asymptotes in there. It's got looks like a saddle point, it's got a cusp, it's got all kinds of stuff. So let's take a look at how to draw something like this. For one, if the original function has vertical asymptotes, it's undefined, then the derivative is going to have those same vertical asymptotes. If the graph doesn't even exist at those spots, then the derivative can't exist at those spots. So just either redraw them or just obey those asymptotes. Now let's think about this. This portion right here. Now we said we're going to look for zeros, look for relative maxes and mins, the critical points on f, and we're going to make those the zeros on f prime. So this portion right here doesn't have any places where it's perfectly flat, any horizontal tangent lines. So maybe I'll come back to that. This portion in the middle, that little downward curve there, definitely has a place where it's got a horizontal tangent line. It looks like it's right at 0. So what I'm going to do, I'm going to, right in line with that, I'm going to make that a 0 on f prime. The slope right there is 0, f prime is 0. So we make it a 0 on our f prime graph. Do we have any others here? If you look over here, you've got another spot right there, another saddle point. The slope is 0 at that spot, so I'm going to try to line it up and make that a 0 on f prime. And I don't think I have any other zeros, but you do have another critical point in a sense. You've got this cusp where f prime will not exist, so I'm going to have some kind of hole or vertical asymptote at that spot. Okay, let's see what's going on here the rest of the way. Maybe let's start here in the middle with that first critical point. That should be pretty easy to kind of handle this, that f prime, since f is changing from increasing to decreasing, f is changed from increasing to decreasing, then f prime should be changing from positive to negative, right? So I'm going to draw something that is above the x-axis and goes below the x-axis at that spot. And you're boxed in by those asymptotes, so I wouldn't worry about what kind of curvature you have, really. I mean, that's pretty bad drawing, but you try drawing this on an iPad. Almost like a tangent graph there. Cotangent graph, I should say. There you go, something like that. You're going from above to below the x-axis to show f prime is changing positive to negative. Okay, how about this portion on the left? There was no place where f prime was 0, right? No horizontal tangent line, so there are no zeros on my f prime graph here. But okay, let's dig deeper. So it doesn't touch the x-axis, but f prime, what is it doing? Well, just look at f. F is increasing, right? F is going up. It's got positive slope, if you want to say it that way. F is increasing, so f prime should be positive, should be above the x-axis, that whole region. So it's really going to be kind of almost right on top. You could try to squeeze it in a little bit to the left or to the right if you want to see it better, but you're definitely going to be above the x-axis the whole way. And the slope on the left side is approaching 0. It looks like there's a horizontal asymptote. So your f prime graph should be getting close to 0, kind of obeying that same horizontal asymptote. So just to distinguish it a little bit, I'll draw it a little further away. But again, that I would have trouble judging without some scale or some numbers or the equation about where exactly this curve should be. Should it be tighter to the original? Should it be, closer to the asymptote? But I know it's doing something like that. So there you go. Problem solved there. And now, how about this big old mess over here? You've got this. It looks like a polynomial, like a cubic function, is all of a sudden changing right into a line segment with a negative slope. So let's try to basically capture that. So our saddle point here is our 0. Before that, f is increasing, so f prime should be positive. So my f prime should be above the x-axis, right? I should be above the x-axis. And at that spot, the slope is 0, so I'm going to hit 0. But after that, f prime is positive again, so I'm going to bounce right off the x-axis and stay positive. So We've seen that, just in the last problem, but when you have that kind of saddle point, your f prime graph should not be crossing the x-axis, should be kind of bouncing right off of it. So something like that. And now, here's the thing, right around wherever you end up drawing, again, I could be a little higher or a little lower depending, but at the x value that lines up with this cusp, your graph should have a hole in it. Your f prime does not exist at that cusp. Because what's happening is, I don't know how high this spot goes, maybe it would have been there, maybe it would have been up higher, but all of a sudden it's dramatically, instantaneously changing to a line segment with a negative slope. So all of a sudden my f prime is going to jump below the x-axis, right in line with that same x value, and it's going to be another hole, right? And we have a negative constant, kind of tying into the first example where you're just thinking about the slope of that line segment, which is a negative constant. So I'm drawing a negative constant. How far below, that's tough to tell, but something to that effect. And so I would say that's a pretty decent f prime graph, what I drew there in red. And so there you go. I mean, sometimes you just have to take it piece by piece and do your best with it. Some of them can be pretty weird. So there you go. There's 3 different examples of varying difficulty. If you have any questions, let me know or ask in the comments, and keep working hard and hanging in there.